You open a new 9-page model card from Google DeepMind, Gemini 3.7 Flash. You want to answer 2 simple questions before deploying it. Is this model capable? And is it safe? Normally, you'd feed this PDF into a text ingestion pipeline to pull benchmark numbers, but doing that here will immediately break your analysis. The most critical part of this document, the capability and pricing table on page 5, is not text. It is embedded as a flat image. To an automated text parser, every benchmark score is just a blank void. Then you hit the second roadblock. Search the text for foundational specifications, like the architecture, the training dataset, or the hardware used to build the model. They aren't there. Even the safety section masks the raw data. The executive summary claims performance is similar to the last generation, but the actual data tables underneath show distinct numerical regressions. DeepMind formatted this as a delta card. It is designed to document only the specific changes since the previous version, rather than providing a full specification. Auditing a release like this requires abandoning the idea of a single spec sheet. You have to execute a multi-document forensic audit that actively bypasses the public relations framing. This chart shows exactly how a delta card works. For the architecture, the training data, and the hardware, the document explicitly instructs you to see the Gemini 3.6 Flash model card. It inherits its foundation completely. The actual technical changes claimed in this new document amount to 2 sentences: algorithmic improvements to its core reasoning foundation, and customizable thinking configurations. The card does define the exact interface. You get a 1 million token multimodal input window and text output capped strictly at 64,000 tokens. But those algorithmic improvements to the reasoning core are never given an operational definition. There are no API specifications or recipes explaining how the model was actually altered. To evaluate the model's true utility, you have to ignore the prose summaries. You take that declared interface and map it directly to the transcribed benchmark grids. Because those benchmark grids are locked in an image, you have to manually transcribe the numbers before you can run any actionable comparisons. This chart shows the same family comparison. Weighing 3.7 Flash strictly against its predecessor, 3.6 Flash, the results are definitive. Look at the long horizon tasks. DeepSWE jumps from 48.6 to 65.3. OSWorld moves from 33.8 to 47.9. Out of 18 reported rows, there is only 1 regression. It dips a minor 0.7 percentage points on the CharkSive chart reasoning benchmark. We don't have to math behind the update, but this near-total sweep confirms the underlying reasoning core was materially upgraded. Beating last year's model is expected. The actual routing value of this release depends entirely on how it performs against external frontier models. Next, we pit 3.7 Flash against Claude Sonnet 5, GPT 5.6 Terra, and Muse Spark 1.2. This visual shows the split profile. On the left, 3.7 Flash achieves best-in-table performance for code quality, legal workflows, PDF document comprehension, and long context processing. On the right, it definitively trails frontier leaders in long-horizon agentic software engineering, losing to GPT 5.6 Terra, and falls behind Sonnet 5 on desktop control. This chart shows the initial output economics. 3.7 Flash enters the market at an introductory price of 75 cents per million input tokens and $3.75 per million output tokens. At launch, that pricing means you are paying roughly 1/3 of what the frontier competitors charge.
But read the footnotes. The introductory promotion expires December 31st, 2026. On January 1st, 2027, the price doubles to $1.50 in, $7.50 out. You are then paying 75% of Sonnet 5's output price. Then there is the customizable thinking knob. This feature lets you trade latency for higher quality on a per-request basis. Deeper thinking burns through your output token budget. Because the card provides 0 specific API cost curves, your exact spend per request is completely unpredictable. The cross-vendor performance split and the impending pricing cliff turn model selection into a time-sensitive financial routing decision. The safety section requires exact scrutiny. The executive summary claims similar performance with low unjustified refusals, but you need to check the raw data. Read the direction convention column first. Some rows measure safety where higher is better, others where lower is better. Applying these conventions, the reality is mixed. 2 metrics improve, 1 remains flat, and 3 show regressions, like a 0.84 percentage point increase in unjustified refusals. Furthermore, the engineers actively changed the grading criteria between the 3.6 and 3.7 releases. That breaks any strict comparability between the old and new cards. The release relies on manual red teaming to backstop these numbers. Human reviewers found that the automated regressions were overwhelmingly false positives or non-egregious errors. The phrase similar safety performance is accurate enough, but it successfully masks granular regressions and shifting evaluation baselines. The industry has moved away from binary safe or unsafe labels. Google now relies on the Frontier Safety Framework to continuously monitor capability risks. The baseline requirement for launching this model was met. 3.7 Flash did not reach any tracked or critical capability levels. But this grid highlights a hidden tension within that framework. The model successfully triggered intermediate alert thresholds in 2 distinct risk domains, CBRN and cybersecurity. In the CBRN domain, a subset of expert red teamers successfully elicited accurate and actionable information across a full harm journey. Hitting those alert thresholds mandated that updated, domain-specific safeguards had to be implemented before the model could be distributed. Yet the most startling technical observation in the document sits quietly in the ML R&D section. Gemini 3.7 Flash exhibits stronger situational awareness than its pro-tier predecessor. It accurately observes and detects when it is operating inside a constrained testing environment. The limitation keeping this below a critical capability level is simple. It knows it's being tested, but lacks the agency to bypass those restrictions. Safety assessments have shifted to managing proximity to critical thresholds and monitoring behaviors like situational awareness. Auditing an iterative frontier model release requires dismantling the document structure. You have to bypass the marketing copy to extract the raw data. First, Delta cards delegate depth. Your audit is a chain of predecessor documents. Second, benchmark numbers hide inside image traps that break ingestion pipelines. You must manually transcribe them. Third, track intermediate alert thresholds and self-awareness markers, even when critical limits hold. And always factor in hard pricing cliffs when calculating the long-term utility of a new API. Engineers must now optimize for specific capability profiles per dollar while operating within these monitored risk thresholds.